spin excitation do reside in the superconducting material. So here, he's going right through the dome, and that excitation hasn't gone to zero. Remember, the most fundamental understanding is that magnetism destroys superconductivity. So we were thinking that this peak here would goes to zero, the blue peak, when you enter the superconducting dome. It doesn't, it persists, it is still here. And well, it's kind of more spread out, right? Here it is more narrow and peaking around that well-defined energy here. Now it becomes broader, and very broad here. That is a signature that you've doped more your sample, but it doesn't go to zero, it is still there. So that was a very important finding that RIXS was able to get to the community, showing, illustrating the power, the strength of the technique. And what I'm going to show here is the energy of this blue peak for the 5 samples as a function of momentum, going so from here to there. So here we go. That here in the reciprocal lattice unit is the momentum, okay? And these here are the different points corresponding to different samples. Well, the message is that, no matter what the doping is, you still have the same dispersion. Even the peak got a little broader, it still goes to higher energy for higher momentum probed. So that's the signature, that this dispersion here, this is the energy of the figure. That dispersion is a characteristic signature of a spin excitation. And again, it is showing that even in superconductor, you have a local spin wave forming. It may not be super long range order at the macroscopic scale, like a strong magnet, but locally, within a few unit cells or maybe a few tens of unit cells, you still have a local magnetic order in the superconductor. And that's in good agreement with inelastic neutron scattering. What I'm saying here is that inelastic neutron scattering would show you, a spin wave dispersion like that, okay, and in a undoped sample. So RIXS was able to now see that spin wave dispersion in the doped sample. What's important to understand is that if you're doing inelastic neutron scattering, which is also a very powerful tool, so you're gonna have to use like a spallation source somewhere. We were not doing neutrons at BNL. You would have to go to NEST maybe, and there you can actually do similar inelastic scattering studies, but because of the nature of neutrons, you cannot refocus the beam, and you got a very big penetration depth. You need to have like really big crystals. So for example, that here is an illustration of what it would take if you were to do that experiment on inelastic neutron scattering. You would have a student spending weekends and nights, and of course weekdays as well, aligning all those different pieces of single crystals, because they're samples that you cannot grow big single crystals out of. Okay, you can only say make a few, like a couple millimeter or even a couple 100 micron big worth, of a sample, and you're gonna need something big like this for neutrons. So you need to have all those individual crystals align perfectly well with respect to one another to be illuminated by or excited by the neutrons. If you do RIXS, you can take maybe one crystal. You can even take a chunk, a small piece, a small fragment of one of these crystals. Our beams, actually at SIX, which is the RIXS beamline at NCLS2, the beam is 1 micron vertical by about 6 or 7 micron horizontal. That is how small it is. So you can really go and study a tiny sample. You could even make a mapping, or you could raster scan your sample to get an imaging information out of that. So this is the, I would say, strong advantage of X-rays over neutrons. The beam size is really small. All right, so we're done with the science examples. Now I'm going to speak about a little bit of how we do, how we've built our instruments at NSLS2. I will not go into details. That will be worth, a different presentation with 50 slides. I just have like maybe 4 or 5 slides with very high-level concepts of how we built it. So that will actually address the question that was in the chat panel about how we could go about, not getting rid, but like really improving the elastic peak, like getting even narrower than what it's at now. So SIX is the beamline soft inelastic X-ray scattering. And so first, when you want to build an instrument with high energy resolution, meaning like a narrow elastic peak, you want your instrument to be very long. And the reason for that is you come in with so-called white light coming off the ring of the synchrotron. So in our case, NSLS2. So it's a blend of different wavelengths, a continuum, okay? And so like white light, okay, out of a light bulb, it's a blend. It's a continuum of all the colors, all the wavelength, the visible range. So that's why it's white. So we call that white light in X-rays. We can't see it, but it's a chunk of continuum of wavelength in the X-ray spectral range. So you have to monochromatize that, meaning you have to select one specific wavelength. Because remember, you want to get that narrow elastic line, and you want to have a very, very narrow distribution of energies around one given energy. So in order to do that, you got to disperse the different wavelength, and do that with soft X-rays using a grating, which is like it's a piece of silicon on which you're gonna scribe some lines at specific distance. It can be, a few hundreds or a few thousand lines per millimeter, and that will have a sort of, it will make like the light diffract. So you come in with white light, and then depending on the angle of scattering, you're gonna have one specific wavelength that reflects, okay, and not the other ones. So this is what is kind of like represented here in a very crude manner. White light comes in your grating, and now you're scattering all those different wavelengths at different angles. So you've broken down the spectrum in an angular manner, if you want. You can see that if you stand very close to the grating, well, the different wavelengths haven't really scattered far away from one another angular-wise, okay? You need to go a little further to let them spread out in order to be able to distinguish them. So the further out you are, the easier it gets to separate the different wavelengths and different colors. So this is what is represented here, but that's one very key component or key ingredient when designing those instruments. You got to aim at something very long to be able to let the different wavelengths spread out as much as possible. Then you can select one with a slit, and it's how we do it. At SIX, we have a grating on the floor of the ring, okay? And then we have a slit, which is 5 micron tall, only 5 micron, located about 50 meters downstream of that grating, okay? So 5 microns, 50 meter downstream, and that will select that tiny slice of the spectrum, rejects everything else. That's how we get, this is one of the reasons why we get a very good resolving power. And what I say here, I say 100,000, that's the resolving power. This is E over delta E, where delta E the resolution. So, we're aiming at 10 MeV resolution for 1,000 eV. So 1,000 divided by 0.01 eV is 100,000. That's the resolving power we're aiming at on the beamline and on the spectrometer. So you need a long beamline, but also a long spectrometer, because on the spectrometer we also monochromatize the rays that got scattered off the sample. So how long is long? So if we, if we look at the spectrometer, the beamline is a different story, but let's look at the spectrometer first. So again, that's here, representing the fact that the further away you are, the easier it gets to monochromatize, right? Here you still just see a blend of the different wavelengths. You're a little further here, you now see one color, and now you green, and now you really separate the yellow and the blue. It's a very schematic way to represent that length, helps you. So originally, like commercial spectrometers in the range of soft X-rays were made just like with a 1 meter length, okay? That's what people worked on for a long time. Then in 2013 or 2014, the SRF in France started to operate a RIXS spectrometer that is 12 meter long. Our spectrometer at NSLS2 is 15 meter in length. So it is, we're leaning in energy resolution, and one of the reasons is the length. And this is where we have here the sample, that's the sample chamber, and this is where we have the monochrometer, actually. with a grating, and the detector is at the end of the arm, and it can rotate here. Okay, so now moving on to the beamline, because we monochromatize both on the beamline and the spectrometer. So the incoming beam coming off the source, which is the ring of an SLS2 here. Okay, so we have a source and insulator that provide us with white light. The monochromator is here, and we monochromatize here. The slit that we're speaking about is here. That's 50 meters separating the two, the graining to the slit. The beamline from source to sample is 105 meters long, and the spectrometer is 50 meters long. So this is, here telling you that the spectrometer can rotate about the sample over 112 degrees. And that is your scattering angle. This is how you vary the momentum transfer. So you measure the energy loss here because you have a grating that monochromatizes the ray scatter off the sample, okay? And you're gonna have the whole spectrum basically projected on your detector, because the grating will basically break down all the different wavelengths and project them onto the detector. That's your energy axis here on the detector. But then if you want to measure the momentum transfer to look at the dispersion of an excitation like spin excitation or lattice excitation, you're going to have to rotate the spectrometer about the sample vertical axis. That's how you do it here on the rails. So long beamline means that would not have fit in the ring building. The space we had on the floor, we could have built a beamline as long as 70 meters. It was just too short. So we had to go out of the ring. That's here a Google map view of the NSLS2 ring with the building that we had to build for the beamline. So if you zoom out on Google Map, you'll see the nano center here, and you will see NSLS2. That's the SIX building right here. This is where the spectrometer is housed. And you can actually zoom out even more, and you'll see we're not that big. There's a collider here, RIXS. So NSLS2 is here, and the building of 6 is here. So being long is one important aspect of it, but it doesn't do it all. You also need to be extremely stable. So the goal is to have that very precious piece of optics, by the way, very costly because it takes a couple of years to polish and to fabricate. Okay, and you have to hold them in a very stable fashion. But you're finding with all the elements around you, like we have the Long Island Expressway less than a mile away from us, the LIE, with potholes, and you see a lot of vibration in the floor coming from that highway. You had the Long Island Railway, which is basically like a train, you know, very, very close from us. Just give me 1 second, sorry. Sorry about that. Trying to do this. I'll have to take care of a baby. I'll be right back. All right, sorry, the baby is still a little unhappy. He found the lecture too long. So let me go back to that here. Okay, going back to that here. Can you hear me?
Yes, we can.
Cool. So yeah, the environment is very harsh. I mean, it's not a bad environment, but you're not going to build a light source, you know, on the moon just to avoid vibration of our environment. You need it to be, you know, basically connected to infrastructure and be in a scientific environment. So a national lab, Brookhaven National Lab is a great environment for it. But again, DLI, we see lots of vibrations coming from that highway with the trucks that are loaded with goods that they bring out east on the island in the morning and back out west in the evening. So that's very bad. We got the a train track not far away, and we feel it very much when the train arrives. And we even feel the shores, the waves, sorry, hitting the shore on the south shore of Long Island, which is like a few miles away. We are even sensitive to that. So how do you protect your optics from all those, vibration pollutions? So we try to decouple as much as possible the instrumentation from basically the floor. So, the building was built on engineered sand. We had like gradients of different densities. We have a very thick slab of concrete built on that engineered sand, which is basically decoupled from all the foundations. Okay, so we have like a rubberish layer all around it that decouples, that avoids any rigid coupling between the slab and the foundation of the building. So if the wind is like hitting pretty badly the walls of the building, you will hear it basically, like it will really basically be inducing lots of vibration in the walls, but that will not propagate back to the floor. And we also have identical concepts applied to the actual instrument. So we have, for example, the optics of our sample chamber, but also mirror chamber, that are directly coupled to very large granite chunks, but it's not coupled to the outer body of the chamber. This is decoupled. It's only coupled via a bellows, which is like a soft coupling. So the chamber might sometimes vibrate, okay? Or it might have it might be like a pendulum. I'm talking about like nanometers, okay? Not microns, not millimeters. We're talking about nanometers, basically. But that will not impact the stability of the optics, which will be in vacuum, rigidly coupled to the granite. I said the optics takes a long time to polish, so everything is important when you are aiming for resolution, okay? The optics can take up to 2 years to reach an atomic flatness, okay? So you want it to be as flat as possible, because if it was to be, a wavy surface, like wavy pattern on the surface, you would end up mixing up all those different wavelengths. So it would basically result in a broader elastic peak. So our optics, when it's flat, is usually like atomically flat. Okay, so that is how, conceptually we were able to reach a very, very high resolving power at SIX. And this is the instrument nowadays. So that's like the downstream part. Remember, it is like total, like from source to detector, 120 meters, but that's like the downstream end of it. The beamline is here. Coming in is the incoming beam with an energy E1 and a momentum K1. The sample chamber is here. And there's a scattered beam here, which is analyzed in the monochromator, where we basically can break down different wavelengths and project them onto the detector 15 meters downstream here. So that is the outgoing beam of the RIXS process, E2, K2. And we probe momentum transfer, delta Q, by basically rotating the arm here on this granite track. So that's how, we vary the scattering angle. That's how we vary delta from the monochromator. So we have world-leading energy resolution, which goes as low as 13 MeV at the oxygen K edge, 540 eV. We've been now into general user operation for over a year, but we've been taking users before that. So we've had users since July 2018. So going on 2 years and a half of user experiments. It's working really well. And it's one of the most, oversubscribed Beamline at NSLS2, not the most oversubscribed, but one of the most oversubscribed. We have other very valuable jewels at NSLS2 that are also oversubscribed, but it's a sign that the Beamline is highly sought after by our community. And this was my last slide. So I know we're a little early. The problem I see that happened here is that I spoke a little too fast, because if it's an interactive class where I will see you, usually you will ask questions while I'm speaking. You will also say if I'm going too fast, but here was nobody to stop me, so I went really fast. I apologize for that, but that is essentially it. These were my slides on RIXS, and now I'll be happy to answer any questions you have.
All right. There are no questions right now. We'll just wait a couple more minutes.
Sure.
There appears to be no questions at this time, so should we just call it?
That's perfectly fine. So I would say people should really feel free to email me, and I believe, actually, not that I believe, I'm going to confirm that right now. In my email address within the first slide, I can put in the chat panel. Where is that? Oh, to all panelists. So, okay, they won't see it.
Yeah.
Is there a way that you could send my email address to?
Yeah, so we'll send the email address to the college contacts.
Great.
And then they could distribute that to their students.
Fantastic. Fantastic. So, because I mean, maybe they'll be thinking over, the slides and have come up with a question later on, and that's perfectly fine. I'll be happy to address any question there are.
There is one question that just came in.
Oh, sure.
How long does the typical RIXS experiment take?
Oh, wow. So yeah, no, you're asking the right question here. I mean, one of the right questions. There's no not right question, but I would say a very suitable question, because RIXS turns out to be a very low throughput technique, and it's probably one of the slowest techniques there's around on synchrotron light sources. So it takes about up to a week to make a full experiment. So, it's kind of, if you're doing X-ray diffraction, you can study maybe 50 samples in 24 hours. If you do RIXS, you will study maybe one sample in up to a week. It can take sometimes less than that. But if you want to get the full high resolution, okay, the higher resolution means you're going to get, the smallest slit possible. So you reject a lot of unwanted photons, like photons with all the energies you don't want to reject them. You go for tiny, tiny bandwidth. And you have very few photons, okay? Then you also have, let's say you want to do the full map. So lots of different instant energies across an edge, lots of different momentum transfers. Now you have to rotate the arm. All of that could take up to a week. If you wanted to do more, fast throughput, you're not so much to high res, you're happy with, say, 100 MeV resolution, which, by the way, was completely world leading up to 5 years ago. Okay, so it's not a bad resolution. And if you just want to do a few energies and a couple momentum transfers, that would be a day and a half or 2 days. But usually we try to schedule some of our experiments for up to a week. And it's, so in a way it's good, because, you're not killing yourself at taking very, very fast data, having to stay awake all night. Well, you're going to stay awake part of the night. Don't get me wrong. You want to make sure everything is going well. But it may be that you go to bed at midnight and you come back fresh at 8 o'clock in the morning. And whereas if it's X-ray diffraction, you were given 24 hours, you're going to have to take shifts with your colleagues to make sure you make full use of 24 hours. You take maybe a pattern in 1 second or less than that. So it's a low yield technique with advantages and inconvenience, but this is a low yield technique.
Okay. There's 2 more questions that came in. How does the detector rotating mechanism work to avoid vibrations?
Oh, sure. So first, it does not necessarily avoid vibrations when it rotates. So we don't take data, in a fly mode, like while I was sweep the detector, on the rail. So what's happening is, because RIXS, again, is a very low yield technique, we would move the arm to a certain angle where we want to be, okay? And then we would let it stand down, go quiet, and we'll wait like a few seconds, and then start taking data for whether it's an hour or whether it's a day, depends on the experimental needs. So the vibrations are being avoided once everything is static. Why? When it moves, it doesn't have to be, that vibration free. Now, you don't want it to rattle like hell, otherwise you will lose your alignment. So for that, what we've done is the granite tracks. We have a granite track under. I can actually go back to this here, share screen. We have 2 granite tracks, and we have one here, what the monochrometer of the spectrometer is. There's a granite track, and one here for the detector. So the alignment of the different granite blocks, you can see one block here, the next one here, and so on and so forth. So the relative alignment in height all across this track here was under, I think it was 20 or 30 microns RMS. Okay, so it means that the granite track is absolutely flat. Well, not atomically flat, but down to, again, micron level. Okay, we're talking about RMS here. And it was even better on that small track here. So, it took like a huge amount of effort to get them installed and leveled to that level. But that so avoids, to have like the detector going up and down. But vibrations are really avoided by letting things go static at one given angle. And we have here, so the arm here that couples this monochrometer to the detector, that's pulling things together, right? There's a motor here and one there, and it rotates. It helps bring the 2 extremities one, in concert when it moves. When we go in static mode, there's a retraction of the rigid coupling parts that retract. Okay, so there's no rigid coupling between this long pipe and the monochrometer and the detector. It's only the only points of contact are through bellows, which are soft. So if you have, say, vibrations in the pipe, because it can act as a pendulum, an antenna to some extent, they won't be transmitted that much here and there, because again, the rigid hooks that bring everything together are retracted once the spectrometer stops moving. So it's another way to avoid vibrations in the static mode when we measure.
All right. And can you go once more over the recent for the wavy band gap versus momentum from one of your first slides?
Okay. So yes. So let me go back. Actually, let me share first and do share screen. Here. All right. So if you want, what's happening here is those points here in the reciprocal space are kind of, connected somehow to, an interatomic distance or a specific point in a real space, right? You can work that out through Fourier transform. What it tells you is that electrons will not have the same energy, whether they are, at a certain site or whether they're further out of this site. It reflects the fact that the energy of an electron is not going to be exactly the same all across the crystal. So that is telling you basically, the energy of the electron is going to have that spatial distribution, which is encoded in those bands. Again, this is not directly the direct space. It's a reciprocal space, a Brownian zone, but that kind of is correlated and connected with how a real unit unit cell in the real space would look like. So that tells you, again, the energy of the electron has a distribution in real space, which here we study in the reciprocal space. And if it were completely flat, it would be probably a sign that there's really no correlation between electron. It would be like a perfect metal in a very simple structure. But that usually doesn't really happen. You will most likely have those kind of like peaks, crests, and dips happening. So that is, again, the signature that the electrons are very sensitive to the environment and their energy will vary depending on where they are located. And then if there's overlap with other electrons, repulsion, or if there's actually attraction. And so it's it's really interesting. You'll see we call them spaghettis because they really look like spaghettis, and they're quite intricate actually. And it's hard to understand when you just see that, but your eyes can get trained to understanding them better. Like you will notice, oh, here I have a kind of like a cone shape here, and you kind of know what that means for the velocity of the electron or their mass. But at first, I know it's a lot to take in, but there's a lot of information about the character of the electrons that you can infer based on these shapes.
All right, I think that was the last question for now.
All right.
All right, so if there's no more questions, I would like to thank you, Dr. Jarrige, for doing this. Really appreciate it. And I will pass out your email to the college contacts, and they
Please.
will then pass it on to the students if they have it.
I want to say it was a pleasure to be giving this lecture, and it's a shame we can't actually speak to each other more in a more direct fashion, but in those times, that's what we have to do. And it was great connecting with you all, and I hope you found a little bit of interest in that presentation, and feel free to follow up with any questions to my email address. I'd be happy to answer this question and chat further.
All right, thank you very much.
You will have a wonderful morning, afternoon, or evening, wherever you are in the world.
Thanks.
So bye-bye now. Bye, everybody.
Money.